Welcome. My name is Randy Ellis. In this session, we'll review prerequisites for nonlinear data analysis, and this session will be on linear data analysis. The main concepts for this session are the receiver operator characteristic, or ROC. We'll look at it as a point and we'll look at it as a curve. This curve will give us scores of data. The area under the curve is a common way of evaluating the ROC curve. So a receiver operator characteristic is something that came out of early uses of radar for detecting threats in wartime. So here what we have is we have a radar screen and we have a human operator. So here the receiver is the radar device, so it's all electronics. The operator is a human who interprets the radar display, and the characteristic is an evaluation of the human performance. So what they were interested in when they came up with this concept was they wanted to see how if they varied the receiver or they varied the operator, how the characteristic would vary. For us, we'll look at this in linear algebra. In a previous session, we went through the confusion matrix where we basically totaled up the number of true positives, true negatives, and so on. Now what we'll do is we'll make this relative. So instead of having true positives, we'll have a true positive rate. And instead of false negatives, we'll have a false negative rate. And then instead of adding up to p, these now add up to 1. Likewise, for the false positives and the true negatives, they'll add up to 1. What that means is we have 4 entries in this, but we have 2 constraints. That means we only have 2 degrees of freedom. We only have 2 things that can independently vary. Normally, what we look at is the true positive rate and the true negative and the false positive rate. So we can, if we only have 2 independent values for a confusion matrix, that means that we can represent what looks like a 4-dimensional object. We can actually represent it using 2 numbers or on a 2D plot. So what does the receiver operator characteristic measure? Well, the inferred terms that we'll use from the confusion matrix are the false positives total is the total number of negatives minus the number of true negatives, and the false positive rate is the false positives divided by all the negatives. And this is called the specificity. So the false positive rate is the specificity, and the receiver operator characteristic is a 2D measure. So we can think of this as a 2D data point or vector, where the first entry is the false positive rate, the second is the true positive rate. This can be presented graphically because it's only in 2D. And each of these values, the false positive rate and true positive rate, are bounded at the bottom by 0 and at the upper by 1, which means that we can say that the ROC vector has to lie within a unit square. Let's look at some data from a commonly cited journal article. First, we have 5 classifiers that are operating on a single data set. So we've got some data set and we've got 5 different learning algorithms that are doing it. Learning algorithm A has a relatively low false positive rate and a moderate true positive rate. Algorithm D, which is looking pretty good, has a near 0 false positive rate and a near 1 true positive rate. Algorithm C has them equal. So here this dotted line is where the false positive and true positive rates would be equal. This is often referred to as the null hypothesis, or the what you would get if you were operating by chance. We'll note that classifier E is quite poor in that it's performing less than we would expect from chance. On the right, what we'll do is we'll suppose that we have a hyperparameter, we'll call it theta, which is very commonly used as a threshold, and suppose that we can vary this threshold and we have 20 values in our data set. Sorry, we have 20 settings for our hyperparameter. We start with a low hyperparameter, and then as we increase the hyperparameter, this is giving us a receiver operator characteristic set of points, and if we were to connect this using a piecewise linear approximation, what we would get is an ROC curve. And again, this diagonal, as in the first example, is the null hypothesis, or you can think of it as a constant response. It always says it's got one label or another. It would produce this diagonal. let's suppose that we're going to analyze fictitious data. By fictitious, I mean I personally made it up. So I was thinking, what happens if we have two variants of a virus, and variant 1 infects most people promptly, and if we were to measure from the onset of their symptoms to days, what we would see is that variant 1 has infected a large proportion of the population by day 4, and then it rapidly drops off. Then suppose that variant 2 is present and it affects almost everybody, but it does so eventually. So it has a much slower onset, and then it takes up to 20 days for some people to clear the symptoms, and by the time 20 days have elapsed, we'll suppose that nearly everyone that we're looking at has got variant 2. So we can now superimpose these and say, is there a way to distinguish, based on the number of days, whether a person has variant 1 or variant 2 of this virus? Well, what we can do is we can say the cumulative detection is the area under the curve. So for example, we might say at day 2, how many people on average would have variant 1 versus variant 2. And what we would see is that after 2 days, quite a few people have variant 1, almost no one has variant 2. So we can look at the area under the curve as the value of interest. And then as we increase the hyperparameter, what we're doing is we're integrating under these curves, and we're collecting more and more people, and eventually everyone has been infected. So how can we look at this using the ROC concept? Well, what we'll do is we'll plot the false positive rate using magenta, and we'll plot the true positive rate using cyan. So now these are the areas under the curves. And what we see is that the false positive rate starts at 0, and then by the time we're at day 20, the false positive rate is 1. And the true positive rate, what we're seeing is it rises much faster and it peaks much sooner. So in this particular example, what we see is the false positive rate is always less than the true positive rate, but that will vary depending on the data that you have. So now what we can do is we can see that these rates are dependent on the threshold that we're looking at the number of days since onset of symptoms. So what we can do is we can plot the ROC curve. And what we see is that on day 2, the areas are both small, and then as we increase the number of days, what we're getting is the ROC curve. And in this example, the area under the curve is 0.86. The very best classifier would have an area of 1. So you could say that in some sense it's 86%. What I would do is observe that this is a slight improvement over the null hypothesis. There's still a pretty big area where errors are happening, and that I would suggest that in this particular data set that time is not an ideal way of diagnosing the variant, and that perhaps we need a different way to distinguish variant 1 and variant 2 of this fictitious virus. So let's summarize what we've got about the ROC curve. Confusion matrix is usually presented as in absolute terms. We can also present it in relative terms, that is, in terms of rates. The key measures we have are the false positive rate and the true positive rate. A 2x2 relative confusion matrix only has 2 degrees of freedom, and the ROC curve is a way to plot confusion matrices as our hyperparameter changes. The area under the curve we can think of as the improvement over the null hypothesis for our experiment.